Hello, and welcome to Logistic Regression in R by me, Dr. Alan Brain. If you have not any exposure to regression techniques previously, then please view the courses Introduction to Statistics Part 1 and 2 and Regression Analysis in R by me, Dr. Alan Brain. Files for this course presentation are available on drbrainstats.com. and please download the file. This course covers sampling data frames to create your build and validation data frames, weight of evidence and information value, binning continuous variables, building the model, testing the model. We're going to test if the model suffers from overfitting, correlation, or reverse causality. There'll be very little theory in this course and all be conducted in an applied manner. So what is logistic regression? Logistic regression is used to calculate the probability of an event occurring. For example, a person responding to a direct mail campaign or a customer defaulting on a loan. In our course, we will be exploring the likelihood of a person responding to a marketing campaign. Before we proceed, I would like to introduce you to the model development framework. As we can see, there are many steps to build a model and are always surrounded by meetings, especially in a workplace. This course will cover the steps 3, 5, 7, 8 and 9. So that we can just jump straight into building the model, we need some coding to be completed first of all. So after you've downloaded the zip file, we need to 1. Import the CSV file into R. 2. Create 2 new variables, num to help with the analysis and target, which is based using the response variable. 3. This is a code that enables us to sample our data frame. And step 4. This uses the values created in 3 to create our build and validation data frames. And for our final prerequisite, we're going to investigate weight of evidence and information value. The weight of evidence compares the non-target over target ratio for that bin against the total non-target over target ratio for the whole of the database. The figure is then converted by using natural logs. Information value calculates how well the variable overall discriminates the target variable. And as we can see, the equation for IV contains the equation for the weight of evidence. First, we're going to calculate the weight of evidence using a fictional variable that has been binned into 5 groups. Column A represents the bin. Column B is the number of non-targets. Column C is the number of targets in that bin. Column D is simply B divided by C. Now E uses a total from column B divided by the total of column C. Column F then compares the ratio of each bin between column D and column E. Column G now applies the natural base log to column F. So this gives us our weight of evidence value. As mentioned previously, information value contains weight of evidence. So now we can see, applying the formula, as long as we add up all the values for the IV for each bin, we can get our information value. Any variable that has an IV less than 0.1 should not be considered for the model build. This reduces the complexity of the model and overfitting. Also, any variable with an IV over 0.7 should be investigated, as they could be very similar to the target variable, therefore artificially increase the strength of the model. Which now brings us on to binning the key variables. Rather than just talk through code, I will just explain each step. So the first step, we just ensure that the appropriate libraries have been activated. Number 2, we will create a new data frame with a target variable, ID, and the predictive variables. 3, we can now got a shortcut to bin all the variables on the data frame. Number 4, applies the bins from 3 onto the data frame build 1. Main bank balance needs amending due to its initial binning, so it has been removed from the data frame. At step 6, we have recreated the bins for main bank balance as detailed. As with all model development, we have to treat the validation data frame exactly the same as we do for the build data frame. So therefore, we have to bin the valid data frame as we had the build data frame. So we have removed about 70% of the project time to get us this far, as we moved out steps 4 to 7, which involves plenty of data cleansing. And now we start our logistic regression using backward selection criteria. So step 1, this includes all the variables we want to model. Note all the variables are surrounded by factor and brackets, as we have converted them into categorical. Now with a backward selection, this tells R that we want to conduct a backwards reduction technique on full mod. At step 3, the summary function produces a final model in our output. And so now we're given our initial results. Credit card has been dropped from the model due to being unpredictive. Additionally, you may notice from the results that not all the bins are showing. There is one bin missing from each variable, which is given a value of 0 for the estimate due to R creating our dummy bins for us. If R included all the dummy variables, then a model will suffer from multicollinearity, or sometimes known as the dummy variable trap, as they will be able to predict one from each other. Technically, these are the variables for our model, but without any testing, we are not sure if they should be used. As shown, creating a model is very simple and straightforward, but now we need to know if it's any good. So this brings us to a measurement, and we can use area underneath the curve and Gini. The area underneath the curve produces a score between 0 and 1, and a score of 0.5 means that there's no power. With any values closer to 1 means it's stronger. And then the most common use measurement technique is called the Gini, or sometimes the sum as D. The Gini measurement tells us how well the model separates the targets and non-targets. And this is an example of the graphs. As you see, for AUC, it is all of the chart. With the Gini chart, it's just the area above the line. So how do we calculate AUC and Gini in R? Well, R does not provide the model performance and the results, so we must write more programming code to calculate these measurements. To calculate AUC and Gini statistics, we need the probabilities applied to the model data frame. But first, we need our final logistic model. So step 1, we're going to create our final model with a credit card variable omitted, and then we can use R to apply our probabilities as shown here. Our second stage is calculating AUC and Gini. Now Perfer contains the AUC value that we can use to calculate the Gini, as shown. Now you may have different AUC Gini values, as it all depends on the sampling conducted at the beginning. Now, overfitting. Overfitting tends to occur when there are too many variables or bins compared to the number of targets. This tends to produce a model that is counterproductive to common sense and will not perform to the same standard on a different data frame. A simple test to measure overfitting in a model requires using the validation data frame. The validation data frame must be binned exactly as a build data frame. Then a comparison of the Gini scores is conducted to check if they are similar or within 1% of each other. Now this is our code to score up the validation data frame. We do not create a new model on the validation data frame. We apply the model created previously onto the validation data frame, then use that to calculate our Gini. Now as we can see, with a slight increase in Gini between a build and validation data frame, this tells us the model may not be stable. It does not change dramatically, but allows us to introduce bootstrapping. Bootstrapping involves taking a random sample of a validation data frame 100 times to check the ranges of the different Gini scores calculated. A function has been created as shown on the slide. And from this, we want our quantile results. The table contains the quantile Gini scores from 100 different samples. The build model Gini was 0.645, and using results from above, we can see that it falls within the upper and the minimum quartiles. If the bootstrap method fails, then we need to consider the following. Either remodel the data frame that excludes certain variables until the Gini stabilizes, or return to the beginning and resegment our build and validation data frames. But for now, we can proceed to the next test. Our next test to consider is correlation. Correlation between variables can cause issues. Correlation occurs when two or more variables behave very similar. When this happens, the variables are more likely to predict each other rather than the target variable. We did not conduct the correlation analysis previously, as we did not know which variables would be in the model. Removing variables earlier may remove strong predictive variables and leave a less powerful but still predictive variable behind. Correlation analysis is conducted as follows. First, we'll add the WE values based on original bins using R. We calculate the WE for the main bank balance, update the data frame with these new values, and use R for the correlation test. There is a lot of code on this slide, and I am not going to go through it. What I can tell you is that this code is available on a zip file. And rather than describe the different steps, we can now go to the next slide, which shows us the actual results in Excel. With the results exported into Excel, from below using conditional formatting, it's easily observed if any variable suffers from correlation. Obviously, the variables are correlated with themselves, but not with any other variable based on the plus or negative 0.7 criteria. So the model passes the correlation test. If a correlation had occurred, we'd have to drop one of the correlated variables from the model. This would not make a big difference to the model performance and would mean a more stable and usable model. Reverse causality, our final test. Reverse causality is another important test we must consider when developing models. We need to test that the parameter estimates, coefficients, behave as they should, as in they mimic the target rate patterns. When a model estimates perform opposite to the target rates, this is classified as a reversal. So using our data frame we used previously, core build, we'll calculate the target rates for each bin in the variable with the model estimates. Again, we have a slide with quite a lot of code, which is available in the zip file. The initial data frame to score is called core build. Additionally, I would like to point out how the missing values could be treated. In the scoring script shown, where the value is missing, the lowest score possible is given. Therefore, if we're missing data, then it would be harder for the customer to be contacted. The next stage requires summarizing each variable grouped by the bin. Again, more code, which is also available in a zip file. Here, we are grouping each variable by its bin, and we're trying to calculate the target rate, and we're going to match that back to the score. So then we can provide a graph that shows how everything behaves. And now our chart. First for code, the data frame being used is age. To align the target rate with the scores, this has been multiplied by 5. This is because the second axis is based on primary axis. And then when we go to relabel it, we need to divide it by 5 again. Now we can see from a chart that the estimates perform the same as the target rate, so age does not suffer from any reversal. So rather than print out all the graphs which have no reversals, we'll review an artificial chart with a reversal. Below is a chart created in Excel to demonstrate the reversal. From a chart we observe that the 2024 population does not perform as expected, thus potentially giving those customers a good score. There are two ways to solve this: rebin the variable, potentially making the second bin 22 to 30, or drop the variable. Usually this scenario occurs by the variable reacting with different variables within a model. But, as mentioned before, our model passes this test. So that's it. Producing a model in R is quite simple, but ensuring it is suitable and can be used in a live environment requires a lot of testing. This presentation removes over 90% of work that is normally necessary to construct a robust and powerful model. Thank you. Additional material is available in the R book, available on Amazon, which is very reasonably priced.